tonight might seem a little esoteric, but they're really not complicated. Just don't get overwhelmed and just kind of like go with it. That's just a warning. Let's start off by reviewing. Way back in chapter 1, we talked about matter. We said that matter was any substance that has mass. Matter was composed of atoms, and atoms were composed of protons, electrons, and neutrons. Protons, electrons, and neutrons all resided within the nucleus. Protons were positive, electrons were negative, neutrons were neutral. If you have the same number of protons and electrons, you have a neutral species. That's as many pluses as you do minuses. We looked at a rendering of the helium atom. Now we're going to come back to this a little bit later, so pay attention here. The nucleus of a helium atom has 2 protons and 2 neutrons. It's surrounded by an electron cloud, and we said last time we talked about this, that this nucleus was a teeny tiny little speck in the middle. The cloud is a big cloud surrounding the very teeny tiny nucleus. Virtually all of the mass in an atom is contained within the nucleus. The electrons contribute very little to the actual mass. We talked about the periodic table. Come back to that again. And we talked about the concept of the atomic number. The atomic number, which you'll see up there on the periodic table, is the number of protons in the nucleus of that particular atom. Now, it's important that you remember that the one thing that defines what an atom is the number of protons in the nucleus. That's its atomic number. It doesn't matter how many protons you have or neutrons you have, how many electrons, it all comes down to the number of protons. Anything with 6 protons is a carbon atom. We express this using what we call the atomic symbol. The atomic symbol, you recall, we simply put the symbol for the element from the periodic table. As a superscript, we put the mass number. Now remember, mass number was the number of protons plus the number of electrons. Protons plus neutrons. Down here as a subscript, we put the atomic number. That's the number of protons. Now we looked at an example, and that was carbon. We talked about isotopes. Isotopes are elements with the same number of protons, so the same atomic number, but they have different masses. They have different masses because they have different number of neutrons. For carbon, there are 3 isotopes that are common: carbon 12, 13, and 14. Carbon 12 is a common isotope. About 1% is 13, a tiny trace is 14. This is an abbreviation. Again, these are all carbon, but they have different masses. They're all carbon because they have the same number of protons. They just have different mass numbers because they have more protons. We also looked at this particular image of carbon. Now, we're going to come back to this later. When we talked about this the first time, we pointed out that there were 2 layers of electrons here. There was one particular group of electrons that were close to the nucleus, and another that were separate. Two separate energy levels. Today we're going to figure out why this happens, and we're going to understand why we care about, especially, the electrons in the outer, lowest energy orbitals here, surrounding the nucleus. When we're talking about isotopes, it's fun to think about subatomic particles. This is kind of an introduction to radioactivity, which we're going to cover in much more detail in chapter 11. But subatomic particles are associated with radioactivity. The first report of the concept of radioactivity was about, in the late 1800s. This is a photographic plate. Now, in those days, doing a photographic plate was a big deal because you had to take your glass, you spread an emulsion, you put another glass on top, etc., etc. It was a big, big deal. And somebody noticed that every time they did this and they put a bottle of uranium salt on top of it, that it was ruined. There were big black splotches on it. The big black spots were referred to as fogging. These are due to the radioactive decay of the uranium. Well, Marie Curie, who died doing all this work, was one of the people that helped explain exactly what was happening. Turns out that radioactive substances emitted particles from their nucleus, and that these particles were what was coming out and fogging these plates, etc., etc. Three particles that were identified, and there are many more, but three particles were alpha, beta, and gamma particles. Alpha particles, here, if you look at this, this has 2 protons and 2 neutrons. This is the same thing we saw in the helium nucleus, isn't it? Beta particle, this is an electron. Now, why in the world is an electron doing in the nucleus here? The nucleus is a little positive center. In chapter 11, we'll talk about how the electron manages to get out of there. But the electron, it turns out, or the beta particle, has a -1 charge. It has a very, very, very low mass. The alpha particle, because it has 2 protons and 2 neutrons, has a +2 charge, and it has a mass of 4. Now, as you look at these things, the subatomic particles, alpha, beta, and gamma, differ not only in their mass and their charge, but in their energy. Alpha particles are heavy, mass of 4, and they're not very energetic. They are, however, extremely toxic. Extremely toxic. Alpha particle can be stopped by a simple sheet of paper. Beta particle, this is essentially an electron. It has more energy, it could go through the paper, but not a whole lot more. Gamma particles, very, very energetic. This is supposed to represent about 10 centimeters of lead, and they just pass right through it. Gamma particles, very, very high energy. Gamma particles are photons, that's light, except very, very high energy. Alpha and beta particles are what most things commonly emit. Like I said, alpha particles are very, very toxic. Plutonium, polonium, they are alpha emitters. If you had a milligram of pure plutonium and you spread it around everyone here on campus, everyone would die. 1 milligram. The reason is that even though these are very low energy particles, they tend to be ingested easily, inhaled or whatever. Once they get in your lungs, they sit there and they just shoot these little alpha particles at the wall of your lungs, your DNA, and as they do, they degrade the DNA. Polonium is probably the worst. Plutonium is certainly very bad. We can detect really beta and gamma particles using what's known as a Geiger counter. Again, chapter 11 will go into this in much, much greater detail. As these particles enter, they're called ionizing radiation. As they pass through the gas in the Geiger counter tube, they ionize it. That allows high voltage to arc between one and the other electrodes. And when they do that, you get a little click, and it shows up on a reading. Virtually any nucleus that is unstable enough to give off alpha, beta, or gamma particles is referred to as radioactive. Now, alpha particles, like we said, consist of 2 protons and 2 neutrons. And again, this is the same thing as a helium nucleus with no electrons. So a +2 charge. Has a mass of 4 and a charge of +2. A particle that is very commonly associated with radioactivity like this is uranium-238. Now again, this is a atomic symbol. U is for uranium. This is our mass number, and here's our atomic number. Uranium lives over here on the periodic table. Atomic number is 92, so 92 protons in the nucleus. Now this nucleus is unstable enough that it will spontaneously lose an alpha particle. So that's two protons, 2 neutrons. This is abbreviated as an He, so helium, mass number of 4, atomic number of 2, 2 protons. And when it does that, we will form thorium. If you look at this, this is called a nuclear equation. In a nuclear equation, this is also abbreviated sometimes as an alpha for 2. I would typically do He. So either one will show up. Sometimes this will show up on a quiz. Typically on exams, I would do this one. So look at this equation here. We started off with uranium with 92 total protons. This loses an alpha particle, which is 2 protons, and forms thorium. Thorium is over here. There it is, right there. And it has an atomic number of 90. We start off with 92, lose 2, and wind up with thorium. Likewise up top, we start off with 238 as our mass number. We lose 4 and 234. Again, it all adds up to 238. The thing about an atomic equation is that the number of protons and neutrons on both sides must be the same. Here we had 92, that's the same as 90 plus 2. Up top, we have 238 on this side, 234 and 4 on this side. An atomic equation, a nuclear equation, just like a chemical equation that we'll see must be balanced on both sides. For a nuclear equation, we're balancing mass number and protons. Now this is kind of neat. This leads us to the concept of nuclear fission. Once again, chapter 12. But, just as an intro, one of the most important elements with this tendency is 235, uranium-235. When uranium-235 absorbs a neutron, it forms an unstable nucleus. 236 is unstable. Because it's unstable, it splits. When it splits in half, it gives off energy. This is the concept of what we call fission. So here's our uranium-235. What we're going to do is take a neutron and we're going to shoot it at it. So it actually hits this nucleus. It will be absorbed by the nucleus and we'll get uranium-236. 236 is a bad number. Here it comes. Splits apart, lots of energy, and we also produce 3 neutrons in the process. Now, the nuclear equation describing this looks something like this. We're starting off with uranium. We're adding a neutron. We split the nucleus in half. We get krypton, barium, and 3 neutrons. High energy neutrons, and we also get a lot of heat. If you look at this in terms of a nuclear equation, in terms of mass numbers, we have 235 plus 1, that's 236. On this side, we have 91, 142, and 3, and that also equals 236. So the nuclear equation is valid. The mass numbers work straight across. Same thing with atomic numbers, 92, 0, no protons and a neutron. 36 plus 56 equals 92. So we simply split this thing in half. Now this is important because this process can lead to what's called a nuclear chain reaction. Nuclear chain reaction. We start off with 1 neutron, 1 uranium, and we make 3 neutrons. If you have a lump of uranium-235 that's big enough, each of these neutrons will do this again. And they'll make 3 more neutrons. And they will do it again. And you get 3 more neutrons, etc., etc., etc. This is called a chain reaction. The classic way to show this is with ping pong balls. Now what we have in this video when I started is going to be a little box with mouse traps. And on each mouse trap is a ping pong ball. We will drop 1 extra ping pong ball in, that's our neutron, and boom, they all go very, very quickly. This is the concept, again, of a chain reaction. And this is the concept that gives us a fission bomb. We start off with uranium-235. We initiate the chain reaction with 1 neutron, and all of the energy that's evolved is expelled as a chain reaction occurs in this fission bomb reaction. In chapter 11, we will talk about this and exactly how easy it is to to make one of these. It really is. You could do this in your basement if you had the right stuff. All right, let's go back to our opening slide, talking about elements, atomic structure, and stuff like that. These are experiments by Rutherford a long time ago. And using this, he was able to actually measure the diameter of the nucleus of a gold atom. It's kind of an amazing experiment. The way he did it was, he took an alpha particle source. Now this could have been, probably was, uranium-238. We know that it gives off alpha particles. These were directed in a beam through a pinhole at a sheet of gold. Now gold is the most malleable of all metallic elements. That means you can take gold and you can pound it so thin, it is essentially one atom thick. It is, you can just do this with gold, it's just amazing. When you see a church or something with a nice gold dome on it, that's gold leaf. You take virtually no mass of gold, pound it out, stick it on, it's very little mass, but it's solid gold. Gold can be pounded, it's malleable, the most malleable of all elements. So what he did was he took the alpha particle source through a pinhole and then shot it at a gold foil. On this end he had a fluorescent detector. So every time the alpha particle hit, it was a little flash of light. In the movie here, you see alpha particles coming. Now these are positive, aren't they? The nucleus is positive, so they repel each other. As these things come and encounter the nucleus, they're deflected. They're deflected back at various angles, and those are all recorded on the fluorescent detector. From that, he was able to actually calculate exactly the size of this little gold nucleus. Turns out the nucleus was about 10 to the minus 15 meters. 10 to the minus 15. That's a really small number. If you compare that with the overall size of the gold atom, the gold atom is roughly 10 to the minus 10 meters. That means that the overall radius here, relative to the nucleus, differ by a factor of almost 300,000. In terms of percentages, 0.0004% of the total space that an atom occupies is this nucleus, and yet that's all of the mass. We've said this before, but again, let's just make sure we understand. Virtually all of the mass of an atom is in the teeny tiny nucleus. The atom itself is huge. This is a tiny speck in the middle. Any questions? Chapter 11, we will go into radioactivity in much more detail, and again talk about fission, fusion, all of those really neat sorts of things.
I have a question.
Yeah.
Where did the extra neutron come from?
Where does it come
The
from?
equation.
Well, you need a neutron source. Where do you get a neutron from? That's actually a good question. There are ways that you can generate a neutron, usually by taking some other element, like a heavy lithium or something. If you compress it with a great force, it will emit neutrons spontaneously. That's called the trigger in a nuclear weapon. All right, let's go back to what we saw just a little bit ago. We've seen this before. This is our schematic for a carbon atom. We said a carbon atom, atomic number of 6, right over there. Most commonly it has 6 protons, 6 neutrons, so a mass number of 12. That's the most common. That's what this represents. And again, it's this tiny dot in the middle. In order for carbon to be neutral, it also has 6 electrons. 6 pluses, 6 minuses. When we showed this picture, we showed it this way as 2 rings of electrons. The core electrons, these are the guys that are closest to the nucleus. They are something we really don't care much about. We don't care about them because they're not involved in the chemistry of carbon. But the outer electrons, these are higher energy. We will see that these are called the valence electrons. These guys are what we use to make chemical bonds. Those are the ones that are interesting. Now what we're going to do is talk about energy levels within atoms. We're going to talk about orbitals. Orbitals are the things that hold the electrons within the energy levels. We're going to do this so that we can understand better the valence electrons around the atom. And we want to do that because those are the things that give rise to bonding. We need bonds between atoms to make compounds. So, let's go on to electron configuration. We talked about the periodic table. When we talked about it, we said there were 8 groups across that we were going to talk about. Some in the middle that we're not going to talk about, but 8 across that we would. We also said that there were periods. Periods went from 1 through 7. Carbon is here in period 2. The period is what tells you how many energy levels you have in a given atom. For hydrogen in period 1, you have 1 possible energy level. Period 2, where carbon is, we have 2 possible energy levels. That is where the electrons will live, either in the inner or the outer shells, going all the way down here to 7. Now, if you let the period number be n, the number of electrons that can exist within that particular energy level or quantum level is 2n squared. So with 1, 1 squared is still 1, 1 times 2 is 2. So in our first level, we can only accommodate 2 electrons. Our second energy level, where carbon lives, we have n squared is 4, times 2 is 8. Down here in 3, we have 18, 32, 50, etc., etc., etc. Within each of these energy levels, the electrons live in what are known as orbitals. Now, the simplest orbital is spherical, called an S. It's a little ball. So electrons live in this little ball. What that means is, in this region of space, you are likely to find an electron. This is called an s orbital. Every orbital can only hold 2 electrons. Only 2. Going up in energy, we have the p orbitals. Now, each of these orbitals, again, can only accommodate 2 electrons. So here we have 2, 4, 6 possible electrons in p orbitals. Look at the geometry here. These are lobes, top and bottom. And what this represents is the region of space where you are likely to find the electron. It could be up here, it could be down here. Interestingly, this is a crossover point. It's never there. It's never at the node. It's either top or bottom, but never in the middle. Concept of tunneling. It gets there without ever being there. Below the P's, we have the really cute ones. These are the D's and the F's. My favorite D is this guy with the donut around the middle. My favorite F, I suppose, is this one with 2 donuts around the middle. Again, these are simply regions of space where these electrons are likely to be found. Now, in this class, we're going to be concerned only with the S and the P's, because these can get really bizarre, but they're cute to play with. What I'm going to do is look at the periodic table. Remember how funny our periodic table looks? And we're going to explain why it looks that way based on orbitals and energy levels. Our first energy level here, going across, this is hydrogen and helium. Because it's level 1, we can only have 2 electrons. That means we have 1 electron for hydrogen, 1 electron for helium. First energy level, only 2 electrons. The lowest energy orbital is an s, so both of these are in what we call the 1s orbital. Next, we have this guy, our second energy level. That's where carbon lives. The first 2 electrons down here go in what's called the s orbital. So this is 2s. We have 1, 2 electrons. Now remember, we can have a total of 8. So the other 6 go in these guys. 1, 2, 3, 4, 5, 6. And these are our p orbitals for the 2s level, for the second energy quantum level. 2s and 2p. For the third, again, we're here and we're here. First 2 electrons go here. Now, this can hold a total of 18. But there's kind of a funny thing about the 3d orbitals, which would be here, that they're off in their energy. So we don't see any elements with these 3d electrons. Instead, we only see 3p's, again 2, 4, 6, and these do not form until down here. For our fourth energy level, again, the 4s. Now we fill up the 3ds, and finally the 4p's. Once again, in this class, we're only going to deal with energy levels 1, 2, and 3. So we don't have to worry about D's or F's or whatever. It's important to remember that every orbital can only hold 2 electrons. All right. In addition to it holding 2 electrons, electrons also have the property, quantum property, called spin. Spin looks like the actual electron is spinning. Because it's spinning, it forms basically a magnet, up and down. We represent that using little arrows up and down, depending on north or south. Now this is important because there's something called Hund's rule. Hund's rule says that you put electrons into orbitals one at a time, all with the same spin, so all up or all down. Then you start to pair them within the orbitals, one at a time, and then you do pairs. So for hydrogen, hydrogen is in the first period right there, has 1 electron, has to be in an s orbital. We would write it as this, the 1s, with 1 electron. Helium. Helium is in the first period. It's right over there somewhere. It has 2 electrons. 2 electrons have to have opposite spins, so we would write them like this. 1s, 1 up, and 1 down. The abbreviation that we use that makes it easier, we call this a 1s1 and a 1s2. Within the 1s orbital, we have 1 electron or 2. Any questions? Again, it's a little esoteric, but you don't bear with us here. I think we can work through this. Let's go back to our friend carbon. It's in the second period. Atomic number is 6. So it has 6 electrons we're dealing with. What we want to do is draw a representation of the electron structure. All right, let's look at our periodic table again. Carbon is here, and again it's number 6. It's in our second period. So in order to get to the second period, the first period has to be full. So we filled our first period. This is 1, it's an s orbital, and we have 2 electrons in it. Our second period, we're going to start off here. We're going to put 1, 2 electrons in the s orbital. Then we're going to start filling our p's. We have 1, 2 electrons to put in our p orbitals. Now remember, Hund tells us these have to have the same spin and they're separate. So, here's what I said. We have 6 electrons. First one is full. We're going to have the 2s, which is going to be full. And we're going to have 2 p orbitals. We need to put 2 electrons in them. And so it's going to look like this. There's a 1s. So that's the top of the periodic table. And it's full. 1 up, 1 down. Our second, we hit the 2s. That's the 2 on this end of the table. 1 up, 1 down. Now we have 2 electrons for the p orbitals. So we're starting here, we're going here and here. Only 2 electrons, they have to have the same spin, and they're separate. 1, 2. Now, our total configuration would look like this. The 1s is full, the 2s is full, and we have two separate electrons in the 2p. We could write this in shorthand. Makes it much easier, actually. 1s2, 2s2, that's those guys, and 2p, 2 electrons. If somebody asks you what the electron configuration of carbon was, you can simply say 1s2, 2s2, 2p2. You look at your periodic table, because that's what it all comes down to. The 1s is full, the 2s is full, and we have 1, 2 electrons in the p's. They must be separate. Let's do another one. This is fluorine. Fluorine is right here. It's also second period. Now, because it's second period, first one is full. These guys are full. And in the p orbitals, we'll have 1, 2, 3, 4, 5 total electrons. All right, here's what I said. Second quantum level, the 2s, a 2, and 3 2p's. We're going to have a 2s is full, and then 5 electrons in our 2p's. Hund's rule says they must go in one at a time with the same spin, and then you start to pair them with opposite spins. So, 1s is full, 2 electrons. The 2s is full, 2 electrons. A 2p. Now we're going to have 5 electrons in here, right? Hund's rule says they go in one at a time. Then we start to pair them. These are all up, so we need a down and a down. Our absolute electron configuration would look like this. 1s2, 2s2, 2p, total of 5, 2, 2, and 1. The reason the periodic table looks like it does is because of the way the electrons go in the orbitals. Big gap in the middle here. Look at it this way. Our first period, these are only going to be 1s. Our second period, 2s, and then 2p's. Third period, 3s, 3p's, and then we work our way down. Any questions? It's a funny sounding concept, but it's not really difficult. Just look at your period numbers as you go down. That will give you a quantum level. Remember, the S's are over here, and this is called our P block. Any questions? Let's do a simple problem. Now, these are questions off of old exams. I do this all the time. You know that by now. On this one, I wanted to know the electron configuration for sulfur. Now, on your exams, when you have an exam, I give you a periodic table. So you can look at it, don't have to, try to figure it out here. You have your own. Sulfur. Well, sulfur is S, and it's going to be right here. Now, how do we do this? We look and say sulfur is at our third energy level, right? Now that means that 1 and 2 are full, aren't they? They're full. So how many can you put in? 1. Well, you can put in 2. That's it. All 4 of these are 1s2. Our second energy level. First we fill the S, and that's S2. Completing our second energy level, we can put in 6 electrons, so that's 2p6. Gee, they're all the same, aren't they?
Yeah.
All right, our third energy level is where it gets interesting. We've filled up these 2, haven't we? That's 3s2. In our 3s, we have 2 electrons. So, gosh, they're all the same. Now, in our p orbitals, how many electrons do we have? We have, very simply, it's simple. 1, 2, 3, 4. One, 2, 3, 4. Everything else is full, and we have 4 electrons down here. That's why the periodic table looks this way. How about beryllium, Be? How many s electrons total are there in beryllium? There's beryllium. It's in the second period, so the first is full. How many s electrons in the first? 2. So beryllium, and this is the s block, this has 1, 2. 2 plus 2 is what? 4. Lithium has an atomic number 3. Number of electrons in its first shell. Well, this is a trick question. Okay, it's a trick question, I'll admit that. Let's find lithium. Here it is. What is the first shell? The first shell is the core, isn't it? That's the stuff at the bottom. So if it's in the second, that means the first is full. This is our first shell. We filled it up. 2 electrons. In the first shell, this guy, we have 2 electrons. In the second shell, we have 1. How many pairs of electrons in p orbitals if we have a configuration of 1s2, 2s2, 2p4? Remember, we have 3 p orbitals. We put electrons in them one at a time, and then we pair them. So if we only have 4 electrons, we're going to put it in the px, y, z, 1 each, and then we're going to pair one of them. Px, y, z, we pair 1. How many pairs? Only 1. Remember, they go in one at a time, then you pair them. Highest energy level, Now we're talking the energy level where the atom exists, the period where it exists. So neon. Neon is here in the second period. So we're going to ignore the first, only dealing with the second. How many s electrons in this atom? These are all p's, and these are our s. Only two. One more. Oops, nope, sorry. This is a tutorial, the one everyone's been waiting for, electron configuration. It's a little tricky. Again, these are limited only to periods 1, 2, and 3. What you do with this is each of these are little fields, and you're going to enter a 2, a 1, or nothing. That's it. If you enter anything else, it's wrong. So the question is, for sulfur, what's the electron configuration? Step 1, you look at the periodic table and you find sulfur. It's in the third period, right? So that means the first one is full. How many can it hold? 2. It also means the second one is full. So it can hold a total of 8. 2 in the S and 6 in the P's. Third period, the S is full, and we have 1, 2, 3, 4 P electrons. So how do we enter this? Our 1s is full, that's this one. So we enter a 2. Our 2s, that's these guys, they're full. Can only hold 2, we enter 2. Now our p orbitals here, we have 6 of them. But remember, each can only hold 2. So you have to enter this as 2, 2, 2. Now our third level, 3s, that's these 2. That's full. So that's 2 more. And finally our 3p. We have 1, 2, 3, 4 electrons go in there. They must go in one at a time. So let's start off by saying 1, 1, and 1. Now we have 1 more. So this 1 must actually be a 2. 1s2, 2s2, 2p6, 2s2, and 2p4. Key thing in the tutorial is you can only enter a 1 or 2 or you leave it blank. Okay? Do another. Lithium. Find our lithium. Lithium is in group 1 in our second period. Now what that means is that the first period is full. So this is our 1s. It has 2 electrons. Our 2s is here. We have 1 electron in the 2s. So we're going to enter this. Our 2s has 2 electrons. I'm sorry, 1s, 2s, that's this guy, only has 1. Just remember, this is the S block, This is the p block. 2 electrons in each orbital. Silicon. Silicon is here underneath carbon. Again, it's a third period. That means that 1 is full, 2 is full, the 3s is full, and we have 1, 2. How do we enter it? Our 1s has 2, that's those guys. The 2s has 2. The 2p has a total of 6, but they go as 2, 2, and 2. 3s has 2, and our 3p has 1, 2, separately, 1 and 1. Now again, this takes a little bit of practice to get this one. Work on it. Again, it's 5 points towards the point total on your first exam. If you get 5, and send it to email. Any questions? Now, why do we care about this? We care about this because, as I said earlier, the electrons that are in the highest energy levels, so for silicon, it's these guys, these are called valence electrons. These are the ones that are going to form bonds. Going back to our friend carbon. Carbon is 1s2, so it's full. Those are the core, these guys. They don't do anything. They just sit there. But carbon has 4 more electrons, 2 in the s, 2 in the p. These are the highest energy level. These are called valence electrons. We can use valence, the concept of valence electrons, to explain how simple bonding works. Now to do this, we're going to use something called a Lewis dot structure. Lewis dot structure is simply bookkeeping. We're going to take an element symbol and we're going to put valence electrons around it. It's going to work because it kind of works. It explains in a very simple way how we do bonding, how we make molecules. For example, let's go to our friend carbon again. Using carbon as an example. Step 1, you want to write the symbol for carbon. Now that's a C. Carbon is here. It's in our second period. Atomic number of 6. Our symbol is C. We start off by writing a nice big C. Now, think about the electrons around carbon. The S level, the first level here, the 1s, is full. Those are the core. We don't care about those. We don't care about those at all. All we care about are the highest energy level. And those are the ones in the second period. We have a total of 1, 2, 3, 4 electrons. Now what Lewis said was that we were going to put those electrons around the carbon as little dots, called the Lewis dot structure. The only rule that Lewis imposed was the dots go in one at a time, and once you get 4, then you start to pair them. So carbon has a total of 4 valence electrons. So we're going to put 4 dots around our carbon. This is the Lewis structure for the carbon atom. 4 valence electrons. Doesn't tell us if they're S or P's, we don't care. We have 4 single dots around our carbon. Let's do another one. After we get 4, we start to pair them. So if we did fluorine, fluorine is over here, second period still. So we're going to have the first level is full, we ignore that. And we have in our second level 1, 2, 3, 4, 5, 6, 7 total electrons. Start off with an F. Lewis said, put your 4 dots in first. Now you put in and you start to pair them. We have a total of 7, therefore we pair them like this. 7 valence electrons surrounding our fluorine. This is the Lewis dot structure for fluorine. All it shows is the number of electrons in the highest energy level. Any questions? How do you know how many there are? Remember how we said we're going to ignore all these guys in the middle and just count to 8? Here's the reason. If you simply look at the group number, everything in group 1 will have 1 electron. Group 2 will have 2 electrons. 3 will have 3. 4 will have 4. 5 will have 5. 6, 7, and 8. Now remember when we talked about these guys over here in 8? We said that they were inert gases. Inert gases, also called noble gases. Why? Because they don't do anything. Nobility didn't do anything. The reason they don't do anything is that they have a full shell of electrons and they don't want to react with anybody else. Everything else doesn't have a full shell, and that's why chemical reactions occur. Any questions? Look at the group number. It tells you the number of electrons around the neutral atom. And what we're going to do here is a couple things. We're going to start off with neutral atoms and talk about charged atoms. When we have an unequal number of electrons and protons, we make something that we're going to call an ion, I-O-N. If it has a positive charge, that means it has fewer electrons than it does protons, that's going to be a cation. If it's negatively charged, so it has extra electrons, it's an anion. Now the way you draw a Lewis structure for a cation or an anion is to simply start off with a neutral substance and add or subtract electrons. That's all you have to do. So, let's look at chloride. Chloride anion has a single negative charge. What you would do is find chlorine. It's down here. It's in group 7, so it will have 7 valence electrons. Very quickly on your sheet, draw chlorine in the middle and 7 electrons around it.
Chlorine.
Chlorine, Cl. Now you're going to put the first four in as single dots, and then you're going to pair them up. You should wind up with 3 pairs and 1 left over. Now, as you draw these things, it doesn't matter where your leftover is. Remember, this is just bookkeeping. You could draw it with your unpaired electron here, here, here. It doesn't matter at all. So this is chlorine. This is the Lewis structure for chlorine. Now to make chloride, we need to add 1 more electron. Because chloride has a -1 charge, we need 1 extra electron. So we're going to bring it in, pair it up with this guy, and we have Cl-. Now, think about what we have done here in terms of electron structure. We start off here with chlorine with 7 valence electrons, right? And we make Cl-. That means this now has the same number of electrons as argon does here. We have duplicated the structure of the inert gas. We've added an electron. It is no longer reactive because now it has the same structure as the inert gas argon. Let's do it again. Sulfide dianion. You find sulfur. Sulfur is right here. It's in group 4. So it has, I'm sorry, this is 6, isn't it? Group 6. So it has 6 valence electrons. Go ahead, draw the structure. Draw the Lewis structure for sulfur with 6 valence electrons. Start off by putting 1 electron in each top, bottom side, and then pair them until you get 6. And it should look something like that. Doesn't matter if your single electrons are anywhere else, as long as you have 2 unpaired electrons. Now to make the dianion, -2, we simply need to add 2 electrons, don't we? This is sulfide dianion, -2. And what we've done is gone from sulfur here to the same configuration again as argon. This is why they pick up 2 electrons. So they get over here to group 8. One more time, let's do nitride anion. That's N-3. Nitrogen is here in group 5. So put your N and put 5 electrons around it. You should have 1 pair and 3 separate electrons. To make this a -3, we simply add 3 more electrons. And again, nitrogen now has 8 electrons around it, just like neon does. The whole quest here is for these elements to get over here to column 8. One last one. The sodium cation. Here's a positive one. Let's find sodium. Well, sodium is right here in group 3. It will have 1s or 3s electron. 1. We draw our sodium. It has 1 electron, group 1. Now, how do we make this positive? We take that electron away, don't we? When we do, sodium has no valence electrons around it. But by doing so, it's the same configuration now as neon. This is called the octet rule. Elements in a compound will strive to get 8 valence electrons. They want to be just like these guys over here in group 8. They're inert. Chlorine gained 1. When it did, it went from this position here in the table to the configuration of argon. Argon would have 8, group 8. Sulfur gained 2. It went from here, again, over to argon, 8 electrons. Nitrogen, or sodium, we started off here. It lost the 1, so it went from here back up 1 level to neon. The goal here is for these elements to have 8 electrons in their outer shell. It's called the octet rule. When you make compounds, you are shooting to get 8 valence electrons around an atom. Now let me show you how this works in what's known as a molecular compound. This is the concept of sharing electrons. Everyone knows that sharing is a good thing, sharing and caring, right? Well, here's a chlorine. If you isolate chlorine, chlorine comes only as Cl2. 2 chlorines stuck together. Now, chlorine is a group 7, so it has 7 valence electrons, right? Why does it form Cl2? Because what you do is you take another chlorine and you move it up next to it. When you do that, each chlorine atom, now the projector here doesn't do a very good job with this color, but each chlorine atom, let's do this one, has 2, 4, 6, you count both of the shared ones, that's 8 electrons. This guy has 2, 4, 6, the shared ones, make 8. Each has 8 valence electrons. By bonding this way in what's called a covalent bond, each chlorine atom enjoys an octet of electrons. Now, when you draw this, chemists get really tired of drawing little dots. Typically, to show a covalent bond, that's shared electrons, we'll just use a dash. Whenever you see a dash like this tells you you have 2 electrons, these 2, that are shared between the 2 atoms. Now, using this approach, we're going to be able to draw electron configuration for simple molecules. And this is why a Lewis dot structure is important. Later in the semester, we're going to do a lab where we're going to have a worksheet with lots and lots of structures. You're going to draw Lewis structures for all of them. Again, the whole point of this is to make sure that each of the atoms has a total of 8 electrons. Now, the one exception there is going to be hydrogen. Hydrogen is in the first period, right? So it can't hold 8, it can only hold 2. So hydrogen wants to be like helium, 2 electrons. Everything else, we want 8. So let's look at a real example here. If I ask you to draw the Lewis structure of ammonia, what would you do? When you look at the periodic table, you'd see that nitrogen is there. My eyes are so bad I can't see it. There it is. It's in group 5. Has 5 valence electrons. Hydrogen is in group 1. It has 1 valence electron. We have 1 nitrogen, 3 hydrogens. So you start by drawing the atoms separately. You would draw something like this. Here's our nitrogen with its 5 electrons. Here's our 3 hydrogens with 1 electron each. Now, what we're trying to do here is to make sure the nitrogen winds up with 8 and the hydrogens wind up with 2. And we're going to do this by forming covalent bonds and sharing electrons. So after you do this, what you want to do is like scooch the atoms close together. That's what I do. So let's scooch them up. As we do that, we'll see that the electron from the hydrogen pairs with the electron from the nitrogen. These 2 pair, these 2 pair. And so we wind up with a nitrogen that has 8 electrons around it. And each hydrogen has 2 separate electrons around it. This is ammonia. Now remember I said instead of drawing little dots, we'll draw lines. Here's our nitrogen. Each of these lines represent 2 shared electrons. We'll also just call these single bonds. Yeah.
The nitrogen has the 5.
Nitrogen has 5.
Hydrogen has 1. So how did you
So
get
here's our
3
nitrogen with its
hydrogens
5.
up there?
What we're going to do is pair these 2,
Right. That's
those 2,
But-
and those 2.
Okay, I'm still confused because I know, how did you get 3 hydrogens when it's only 1?
In H3, ammonia has 3 hydrogen atoms. 1 nitrogen, 3 hydrogens.
Right.
So here's our nitrogen, our 3 hydrogens. We're going to form a bond here, here, and here. Now this is really simple. Let's do something that's fun. How about molecular nitrogen? Molecular nitrogen, nitrogen that we breathe in every day, exists as N2, 2 nitrogen atoms stuck together. Very, very, very stable compound. Very stable. Go ahead and draw its Lewis structure. Now we know that nitrogen has 5. We have 2 nitrogens, so we can simply draw them this way. Remember, we want each of them to have 8 electrons. How in the world are you going to do that? Well, we're going to go to my computer here and see if I can make this work. Here we go. Here's our 2 nitrogens, right? We have these 2 electrons. Really, quite obviously, we're going to make a bond here, aren't we? That makes sense. We can share those 2. But that would give us 2, 4, 6 electrons on each nitrogen. That's 6, not 8. So what I'm going to do here is go up here and grab one of these electrons. Remember, this is bookkeeping, so I can do this. And I'm going to move it down here. Gonna grab this one and move it here. Now, how many electrons around each nitrogen? Remember, we count these twice, so that's 2, 4, 6, 7 around each nitrogen. That's good, but it's not 8, is it? So let's do it again. I'll grab this guy and move it up. Grab this guy, move it up. And now what do we have? Each nitrogen now has 6, 7, 8. 6, 7, 8. We have 6 electrons between the 2 nitrogen atoms. Oops. So there's our 2 nitrogens, each with 5. We share so that we wind up with 6 electrons between them. Each nitrogen now has 8. 6 shared, 2 out here, 6 shared, and 2 out here. If we draw this using our line bond convention, we have 3 lines. We call this a triple bond. When we form bonds like this, we can form single, double, or triple bonds. Single bond has 2 shared electrons, double has 4, and our triple here has 6 shared electrons. Now we're going to look at lots of Lewis structures over the course of the next chapter or so. So we're going to review this over and over. Again, it's not a real complicated concept. You're shooting for 8 valence electrons around each of the atoms. Now these guys have shared electrons, don't they? It turns out that when you're talking about compounds, there are 2 classes you need to worry about. These guys that share electrons, we will call molecular. They form molecules. The other ones are going to be ionic. Ionic, we transfer electrons and form ions. So 2 major groups of compounds. This is methane. Methane is natural gas. It has 1 carbon in the middle and 4 hydrogens. In each of these bonds shown here, we have 2 shared electrons. Think about the Lewis structure of carbon. Carbon is in group 4, has 4 electrons, right? Each hydrogen has 1. So we make a total of 8 electrons on the carbon and 2 on each of the hydrogens. When we share electrons, we call those covalent bonds. A compound that has a covalent bond is called a molecular compound. It's a molecule. The other option is here. This is sodium chloride. Sodium chloride, what we do here is transfer an electron from sodium to chlorine. Now remember, that makes sodium happy because it now has a noble gas configuration. And chlorine gains an electron that gives it 8, and it's happy. So sodium is +1, chlorine is -1. These are totally transferred, no sharing. But because they're charged, they stick together. Sodium and the chlorine, opposite charges, they stick together. Called an electrostatic attraction. We have chlorine, sodium, etc., and we make this nice big cubic crystal of these charged particles. If you have charged particles, it is ionic. Now remember when we talked about the periodic table and why some of them are colored. We said it's because there were metals, nonmetals, semimetals, whatever. This is how you know if a compound is going to be ionic or molecular. Let's review. In this periodic table, we have colors. Remember we said everything that was bluish here was a metal. Everything that was blue is a metal. Over here we had the yellow elements. We said that those were non-metal. Now metals conduct electricity, they're malleable. Non-metals do not conduct electricity, and they tend to be fragile and they shatter. In between the two, we have a little group of green guys here that we called semimetals. Silicon is a semiconductor. Germanium, a semiconductor. In between metals and nonmetals. Now, this is important. Pay attention. Write it down, remember it. If you have a compound containing only nonmetals and or semimetals, it will be molecular. That is, it will have covalent bonds. If it only has nonmetals and or semimetals, it is molecular. Period. Covalent bonds. If, however, you have a compound containing a metal at all, any metal, it will be an ionic compound. If it contains a metal, it will be ionic. Any questions? That means you kind of like need to get a feel for the periodic table. Again, these are all going to be metals except hydrogen. These guys are going to be nonmetals, and here we have a border. All right, let's do a problem. If I tell you you have magnesium chloride, is this going to be molecular with covalent bonds, or is it going to be ionic? What you do is you look at the periodic table and you find magnesium. Well, there it is. It's blue. Chlorine is here. It's yellow, but it doesn't matter. This is a metal. Even though this is a nonmetal, this is an ionic compound. If it has a metal, it will be ionic. Now let me do a disclaimer here, okay? Nothing is either all this or all that. There are really funny compounds that you would expect to be ionic, that are molecular, et cetera, but we're not worried about those in Chemistry 100, are we? We're worried about metals, ionic. Non-metals, semimetals, molecular. Do another one. Hydrogen fluoride. Hydrogen fluoride, very interesting acid. Anyone watched, oh gosh, what was the show, Breaking Bad? Remember they dumped this in the bathtub and they threw the person in the bathtub and the ceiling and everything else? Interesting acid. Would you expect this to be molecular or ionic? Well, hydrogen, right here. That's our exception on that end of the thing. That is a nonmetal. Fluorine is here. It's a nonmetal. This is a molecular compound, and the HF bond is covalent. Shared electrons. Let's do another one. Silicon tetrachloride. Look at your periodic table, find silicon. Silicon is right there. Find chlorine, right there. Silicon, that's right, silicon. is a semimetal. Chlorine is a nonmetal. Put the two together, it's a molecular compound. See how simple this can be? So if you were to draw a Lewis structure for silicon tetrachloride, you would know that you have 4 covalent bonds here. Sodium bromide. Sodium. Remember, sodium isn't S, it's Na,
This,
right there. And it's a metal, isn't it?
yeah.
What's our rule? If we got a metal, it's ionic. Now there are lots of elements that exist as multiples of the same element. We've already seen chlorine. Chlorine exists as Cl2, doesn't it? Nitrogen is N2. Sulfur can exist in lots of different ways, but one is S8. The bonds in S8, are they covalent or ionic? Absolutely right. All you have to do is find it. Here it is. It's a nonmetal. The bonds are going to be covalent. Kind of a cute compound, looks like a crown. Any questions? All right, let's do an exam question. See how everybody does. This is an actual question, both of these that are coming. Actual questions off an old exam. Go for it. Are these molecular or ionic? This question was worth 5 points, 1 point each. Our first one, Ni is nickel. Where is nickel? Right there. What color is nickel? It's blue. It's a metal. This is an ionic compound. Dihydrogen monosulfide, commonly referred to as simply hydrogen sulfide. This is the smelly stuff that you get in well water. Hydrogen is a nonmetal, right? Sulfur is a nonmetal. This is a molecular compound. Silicon tetrahydride. Silicon, semimetal. Hydrogen, nonmetal. It's molecular. Sulfur, trioxide. Sulfur, nonmetal. Oxygen, nonmetal. It is molecular. Sulfur trioxide, if you take sulfur trioxide and water vapor. That's how you make sulfuric acid. Sulfuric acid is H2SO4. Water is H2 and an O, and that's SO3. Put them together, you get H2SO4. Calcium hydride, where's calcium? It's a group 2. I can't quite see, I think it's there. It's a metal. It's an ionic compound. One more. CS, what the heck is CS? That's cesium. Cesium, group 1 metals, way down there, very, very reactive. Touches water, it essentially explodes. But it's a metal, it's blue. Because it's a metal, this must be ionic. Diiodine heptaoxide, I2O7. Iodine is here, it's a halogen, it's a non-metal. So is oxygen, molecular. Oxygen difluoride. Oxygen, non-metal, fluorine, non-metal, molecular, covalent bonds. I hope you've been listening to how I name these things, because that's one of the cute things we get to do soon, is to name molecular and ionic compounds. Now, following the convention for naming, CH4 would be carbon tetrahydride. This is also called methane, natural gas. Nobody would ever call it carbon tetrahydride. But carbon, right there, non-metal, hydrogen, non-metal, molecular. And finally, the gimme on the list, sodium chloride. We've seen this all night. Got to be ionic. It's got the metal. Any questions? Now, the whole point of electron configuration was to try to make it clear to you how we can deal with valence electrons and then use these in Lewis structures. On exams, we're not going to deal big time with electron configuration. I know it can be a touch confusing. We might deal small time with it, but not big time. Mostly, we want to understand that elements want to get to the octet, one way or another, and that the group numbers going across 1 to 8 will tell us the number of valence electrons we're dealing with. We can either share these to make a molecular compound or transfer them to make ionic. The one tutorial that you can do for your 5 points for this chapter is the electron configuration. It's a little tricky. Try it. It should work. That's it. On Monday, we will do lab 3. Lab 3 is called sand and salt. Okay? Sand and salt. The instructions in the little lab book say, think about this and develop your own procedure. Well, you know what? I'm sorry, but I'm not doing it that way. I've got a procedure, and it's up on Black